Hello, everybody. Thanks for coming. Welcome to the MIT Category Seminar. So today we have Prakash Panangaden from McGill, who's giving a talk about Markov processing using category theory. This is the third talk in a series, so the other two talks are linked in the comments. And without further introduction, let's welcome Prakash, and please go ahead.
Thanks, Paulo. This is a great pleasure to be able to give the third of these three talks. So originally, I gave this as a series of three talks, but on consecutive days to a captive audience. So basically, this was at Lumini in Marseille, just outside Marseille, and it was on 3 consecutive days, so people had the topics fresh in their minds. In this case, the first of these three was given in April in California, technically. Of course, it was always from my office at home. But the first one was in April from John Baez's seminar hosted at UCR. The second one was at the Categorical Probability Workshop nominally at the Perimeter Institute in Waterloo. And so I'm moving east. This is the third one at MIT. So anyway, I will have to necessarily repeat a lot of things. Of course, I can't repeat everything, otherwise it would be a 3-hour talk, but I will repeat a lot of things. The first part, therefore, will look very accelerated if you're seeing it for the first time, with lots of things brushed under the carpet or or skated over. But the other two talks are linked if you want a more detailed version. Okay, so let me start the actual talk. This is joint work with my former master's student, Philippe Chaput, with Vincent Danos in Paris at ENS, and with Gordon Plotkin, who is jointly at the University of Edinburgh, but also at Google Brain in California. Okay, and what we were doing is developing a theory of approximating Markov processes. So in fact, approximation was our goal. And so all the stuff that I covered in the first two talks was aimed at the new stuff that's here today, which is how we do the approximation. In previous talks, I'd covered this concept of bisimulation, but I will repeat that. I'd even covered the concept of how approximation works and how it's closely related to bisimulation, but I will repeat that as well. The minima realization stuff is new to this talk, and we'll also I'll talk about projective limits. Okay, let's see if this works. Whoops, doesn't work. All right.
So, Prakash, by the way, how would you like your questions to be asked? Will you pause for questions? Would you like people to interrupt you, maybe by writing in the chat, or?
Good point. So probably the best thing is for people to write in the chat, and for some, I guess you're the host, is for you to interrupt me.
Okay, very good. So
if
everybody
there's a question that needs my attention, interrupt me. I think that's better than having everybody interrupt me. But I won't be watching, for raised hands. So
No,
best if
I will.
Do it in the chat.
I will in case. So please raise your hand or write in the chat if you have any question.
Yeah.
Right.
And sometimes I guess you can decide that this is not worth interrupting me for, or it's up to you.
Okay. Thanks.
Okay, so this is a quick
please go ahead.
outline. Sorry, yeah, this is a quick outline. I'll talk about cones and duality, which was basically the subject of the very first of the three talks, and conditional expectation, which in the first talk I showed how to define it functorially. Approximation was introduced in the second of the three talks, and bisimulation as well, but here I'll talk about some things slightly different but closely related, called event bisimulation. And then I'll talk about minimal realization of Markov processes and how that minimal realization is constructed through a logical characterization theorem. And finally, I'll show how the approximations are actually by finite spaces. And then I'll conclude with the conclusion. Okay, so the key point is that one can define a notion of approximation as a morphism, just as bisimulation is a morphism. The approximation morphisms and bisimulation morphisms all live in the same category. So bisimulation is actually a special kind of lossless approximation. Now, The minimal realization amounts to giving a notion of a smallest process in some sense that is bisimilar to a given process. So we'll also define a notion of finite approximation, and we'll construct a projective limit of all the finite approximants, which it turns out, once you construct this limit, will actually give you the minimal realization. Okay, so to begin with, the basic mathematical structure with which we work with are called cones, which essentially combine linear structure with order structure. So if you want to have vector spaces with order, you basically introduce a cone. Once you have an order on a vector space, you get a natural cone structure by asking for the collection of non-negative vectors. So we call this the positive cone, and it has some obvious properties which one axiomatizes through the notion of cones. And if you had a cone in a vector space, it automatically induces an order by saying u is less than v if v minus u sits in the cone. So there's a one-to-one correspondence between defining an order and defining a cone. So these are essentially different ways of defining order structures. Now, many of the structures that we want to look at are in fact intrinsically cones. For example, the collection of measures on a space or the collection of finite measures on a space. These are cones that are not naturally sitting in any vector space. And yes, you can introduce sign measures and make it look like a vector space, but in some sense, that's an artificial extension. So rather than thinking of cones as always sitting inside a vector space, we can think of cones as objects in their own right, and we can axiomatize abstract cones. This was done by Selinger. So in Selinger's axiomatization, you axiomatize something that has something that looks like linear structure, but not quite all the axioms of a vector space. And that introduces the notion of cones. They come with a natural order structure. So the cones that we use, so they look like this. Supposing you have a measure on a space X, then you naturally get the Banach spaces of L1 and L infinity functions. But if you consider the mu almost everywhere positive functions, then these turn out to be cones. Okay, so we'll denote these cones by L with the little plus on top, signifying that we have only looked at the almost everywhere positive functions. Now, of course, I just said cones we should think of intrinsically, and here I am introducing cones that are embedded in a vector space. But the measures, the cones of measures will not come from vector spaces. So supposing you have a measure space where P is a finite measure. By the way, I'm going to look at finite measures, not just probability measures, because one of the properties of cones is that elements in a cone should be scalable by arbitrary positive reals. So of course, probability measures won't satisfy that, but finite measures will. So this peculiar notation with this superscript that looks like much less than px, this means the cone of all measures on the underlying space that are absolutely continuous with respect to p. So absolutely continuous, in case you've forgotten, means that p is absolutely continuous with respect to q. If whenever q says a set has measure 0, then p will also say that. If q is such a measure, we define its norm to be q of x, so the total mass it assigns to the whole space. The collection of such measures is an omega complete normed cone. So let me explain some of these adjectives. Normed, of course, means just like vector spaces can be given norm structure, so can cones, and they have kind of natural axioms of how the norm interacts with the linear structure and how it interacts with the order. Now, omega complete means if you take a bounded increasing chain, then that will have a least upper bound. Okay, so that's the case for these cones. And now the key point is that the collection of this cone of measures and this cone of almost everywhere positive L1 functions are isometrically isomorphic. So there's a perfect correspondence between these cones and those functions. Sorry, this cone of measures and this cone of functions. There's another closely related cone. So this again is somehow cone measures that are bounded by P, but in this sense, upper bounded in some uniform way. So to say Q belongs to this collection of measures means that for some real constant positive, we have Q is less than that constant times the P that decorates the cone symbol. And this family of measures, again, finite measures, is isomorphic to the L infinity almost everywhere positive functions. So we have two kind of Reeds-like theorems that link the cones and the measures. So there's a very nice function which we call the pairing, which takes an element of L infinity plus and L1 plus and defines a real number. So we'll write this with inner product style notation. So you take an F from L infinity, a G from L1, and you get the number associated by this integral. So this is, of course, bilinear, but it's also continuous and, in fact, omega continuous in both arguments. So these two words may be a bit confusing. Continuous means with respect to the norm topology, but omega continuous means what computer scientists like to call Scott continuous. That means it preserves soups of directed sets. Okay, so we'll refer to this map as the pairing. Now, it turns out there are a number of interrelationships between these families of cones. So every one of these vertical dotted arrows actually defines a duality. So L1 plus is dual to L infinity plus. And in fact, the horizontal arrows are isomorphisms. So this square actually just repeats a lot of that information because it says L1 plus is iso to L infinity plus. That's what the star signifies, the dual of L infinity plus, which is of course just saying that this vertical arrow is a duality. And similarly, this isomorphism says that arrow is a duality. So these are duals, those are duals. And this isomorphism, this pair of isomorphisms means the spaces of measures are duals. The basic point is, when you think about Markov processes as measure transformers, you can instead think of Markov operators as function transformers. It turns out this point of view is very advantageous for the development of the theory. So this is roughly 2/3 of the first talk. Just a bit of notation. So supposing I have a measurable function and between two spaces equipped with sigma algebras. Now, if I have a measure on the space X, I'll write this notation M sub alpha P to be the image measure on Y, which is the measure you get by pushing this forward in the natural way. And whenever you have a pair of absolutely continuous measures, so P is absolutely continuous with respect to Q, which means every time Q assigns 0 to a set, so does P. You have a theorem called the Radon-Nikodym theorem, which says the measure computed by P can be computed by doing this integral over Q. And the unique measurable function that mediates this integral is called the Radon-Nikodym derivative, which I will use old-fashioned derivative notation for it. So it looks like I'm doing differential calculus with respect to measures, but it's not really the case. This is just a measurable, almost everywhere unique measurable function, such that if I compute the integral of that function with respect to Q over a set A, I'll get exactly the P measure of that set. So it's a way of relating measures. Okay, that's just notation, all right, now the action that happens where the conditional expectations are defined happens in two categories, which I will call rad infinity and rad 1. So everything actually gets kind of two versions. So there's two versions of conditional expectation corresponding to the, so to speak, the one case and the infinity case. I may only do one in detail and elide the other. Okay, so this has two versions of the theory. So going between these versions by duality is very useful, but that's not my main point today. So let me define the two categories. Rad infinity has objects, probability spaces. The morphisms are measurable maps such that they satisfy the uniformly bounded property. So the image measure of P under alpha is bounded by some real number times the measure Q on the space Y. And the reason for choosing this name, rad infinity, is that if I take a morphism from rad infinity that satisfies this condition, and then I look at the Radon-Nikodym derivative of the image measure with respect to the measure Q on Y, that's going to give me a measurable function that belongs to L infinity. So similarly, the category rad1 has objects probability spaces and has arrows, measurable functions that satisfy this condition. Now the image measure is required to be absolutely continuous with respect to Q. And again, if you look at the image measure and take its Radon-Nikodym derivative, you'll get an L1 function rather than an L infinity function. Okay, good. So let me remind you of the pairing function which mediates that duality. So basically, the isomorphism between L infinity plus and L1 plus star is mediated precisely by the pairing function. So you take f in an L infinity plus function, it defines a linear map on L1 plus by saying, give me a linear map, and I will spit out this integral. Okay, more ingredients. So precomposition with alpha and rad infinity gives a map which I'll call P1 alpha. And this, of course, goes from L1 plus Y to L1 plus X. Of course, because I'm precomposing, the map goes in the contra direction. So alpha goes from X to Y. Precomposing with alpha will give me a map from L1 plus Y to L1 plus X. And dually, given a map in rad1, I'll get corresponding maps, again with the directions reversed. Okay, so the subscripts on the two precomposition functors define the target categories. So precomposition reverses the direction, but the star functor, which dualizes everything in the vector space sense, reverses it again. So P1 alpha dualized will go again from the X to the Y direction. But of course, this time it will take an element of L1 plus star to an element of L1 plus star in Y, and dually in the infinity case. So those are the precomposition functors. And now we're ready to define the conditional expectation value functor. So this is a functor that says, give me a morphism in rad infinity, and I'm going to give you a morphism in this category omega CC, which I forgot to define, I guess, but it's just omega complete continuous cones, normed cones. So how does it work? So given a morphism in rad infinity, the action of the functor is to produce a map from L infinity plus X to L infinity plus Y, and it's simply obtained by composing P1 alpha star with the isomorphisms that go between L1 plus star and L infinity plus. I'll show you this diagram a bit later. So here it is. You start here, duality takes you there. The dual of the precomposition map takes you here, and then duality takes you back. You compose these three, and we take that as the definition of the E infinity expectation value functor. So you might wonder, why the heck is this actually expectation value? So you can look at it in concrete examples, and it will actually turn out to give you the expectation value, which is a detailed calculation I won't do here. As I said, there's an E1 version of this, which I will just flash for you, and you can just see the similarity. Again, it's mediated by precomposition dualized and the isomorphisms. Now, given such a map, given such a functor, we can now define a notion of approximation. So we have this notion of abstract Markov processes. So abstract Markov processes are, again, a dualized version of Markov processes. So what do Markov processes do? They take a point and give you a probability distribution corresponding to one step of the process. However, you can also view this in the dualized sense as a map from the L infinity plus functions to the L infinity plus functions, right? By integrating with respect to the Markov kernel that defines the transition probabilities. So this is the key point. What used to be a Markov kernel that took you from probability measures to probability measures is now a Markov operator that takes you from the L infinity functions to the L infinity functions. So given this notion of Markov process as shown in the top line of this square, we can define a notion of approximating along a morphism. Again, it might seem a bit odd for me to call this an approximation, but hang on for a second. So given alpha in rad infinity, we have the precomposition map. So that takes you from L infinity y to L infinity x. We have the transition kernel here, now viewed as a Markov operator, giving you the transformed function in L infinity x, and then you take the expectation value functor back down to y. So this gives you a kind of cruder version of what's actually happening in x. Okay, so why cruder? Because this expectation value functor will coarsen the information. And so this notation alpha of tau a means this kernel here has gotten weakened or approximated by this kernel down there. So in order to justify that these things really should be thought of as approximations, take two spaces, x sigma, but actually it's the same space but different sigma algebras, where the sigma algebra lambda, I'm sorry, this should be a capital lambda, is a sub-sigma algebra of the sigma algebra sigma. So you can think of it as a coarsened version of the original sigma algebra. So now the measurable function, the identity function in this direction is of course measurable. It wouldn't be in the other direction. And what we're going to do is we're going to use that as the alpha in our approximation. So you see what happens here is that we're kind of injecting the L infinity function into the space of L infinity functions, but with a sharper sigma algebra. Then we're doing the transformation as given by the Markov process tau. And then we're coarsening it back to this space here. And here you can actually see that what the approximation is really doing in this case is taking a function that would be sigma measurable and giving you a lambda measurable version of it. Since lambda is a smaller sigma algebra, the measurable functions are less wild than the sigma measurable functions. So that's the sense in which we're approximating. We're taking functions that might be rapidly varying, sensitive to all the changes that the sigma algebra, capital sigma, can see, and give a coarsened, averaged out or smoothed out version that's only measurable with respect to this weaker sigma algebra. So of course, when you see that it's the same space with the weaker sigma algebra, you can really see that it's a weakening, that it's a coarsening, and hence an approximation. But now the point is, nothing's sacred about maps of this kind. We can look at any old map and approximate along it. Okay, so this is what I have been saying. The approximation of tau is obtained by averaging over the sets of the coarser sigma algebra lambda. Okay, so let me spell out this category. So in rad 1 and rad infinity, the morphisms obeyed fairly mild conditions on the measures, and these were sufficient to develop the functorial theory of expectation value. So if I have a map in rad infinity that's actually measure preserving, it just means that the image measure exactly matches the measure in Q. So we're going to define a category called AMP. So the objects are probability spaces along with an abstract Markov process structure on X. And the arrows are going to be subjective measure preserving maps from X to Y. So that means when I approximate along alpha, I really get exactly the kernel that's here. We're going to define the category rad equals to have the same objects as AMP, but the maps are only measure preserving and of course measurable. So we don't have that condition on the expectation value, sorry, not on the image measures, yes. Okay, so this is the basic arena of conditional expectation and approximation. Let's talk about behavioral equivalence. So this is a concept that has been studied for a long time under the name of bisimulation. And the original definition of Larson and Scow was given for discrete transition systems. And it reads like this. So given a labeled Markov process with a set of states, a sigma algebra on the set, and a Markov kernel now in the traditional sense of a measure transformer, an equivalence relation on the state space is called a probabilistic bisimulation. If you take a pair of related states, then for every measurable R-closed set, the transition probabilities for every possible action must match. So we extended this. This was not how Larson and Scow wrote their definition, because they didn't have sigma algebras and stuff floating around. But we extended this to the continuous case. And this definition captures bisimulation of Markov processes on continuous state spaces. However, if one starts thinking about this, in measure theory, one should focus on measurable sets rather than on points. And I guess this is part of the spirit of categorical probability too, is that points are a pain. There are more abstract ways of thinking about the whole subject. So Vincent Danos proposed the idea that he called event bisimulation. The word event supposed to be evocative of the idea that you're comparing measurable subsets rather than points. And after he proposed the idea, it was developed by him and José Desharnais, Francois Lave-Violette, and myself. So we're going to call a Markov, we've given a labeled Markov process in the traditional sense, with the tau now being a Markov kernel. We'll say that an event bisimulation is a sub-sigma algebra of the original sigma algebra sigma, such that when you restrict to that sub-sigma algebra, you've still got a labeled Markov process, which means that the tau A, when it acts on lambda measurable sets, will produce lambda measurable sets. So you can kind of restrict to a coarser sub-sigma algebra, and you will still have all the same information that you had before. So this is like collapsing it by an equivalence relation, except it's now happening at the level of sigma algebras rather than at the level of points. So when you look at it from the dualized point of view as a Markov operator acting on L infinity plus, it sends the subspace L infinity lambda p, which of course is a subspace of L infinity sigma p, to itself. So again, the diagram you can look at is you embed this into that, you take the Markov kernel acting up there, or you can go here and take the Markov, and then take the embedding up there. So you see doing the Markov kernel down here or in the finer space with the sharper sigma algebra doesn't make a difference. So this means nothing was lost in this case by going to the apparently coarser sigma algebra, at least as far as the dynamics of this particular system. So again, we're going to generalize the notion of event bisimulation by using maps other than the identity maps on the underlying sets. So just to emphasize, this happens precisely when lambda is event bisimulation. It's not true for any old sub-sigma algebra. Okay, so once again, we're going to say, we're going to define a special kind of morphism. So this is a map from this x sigma p to y lambda q, equipped with Markov process structures tau and rho, such that the following diagram commutes. So you precompose with alpha, that gets you here, and then you do the transition as dictated by tau. And that's exactly the same as doing the transition down here as dictated by rho, and then embedding it up there. Okay, so this says tau and rho are really describing exactly the same dynamics. You can either just do it that way, or you can do it this way and you'll find exactly the same thing. So such a map we are going to call, such an alpha we're going to call a zigzag. This terminology comes from modal logic. Now zigzags gives a functional version of bisimulation. So you can ask, what is the relational version? So it's traditional in modal logic and other places to talk about spans of zigzags, but we found out that things work much better to use co-spans of zigzags. Now, if you define bisimulation in terms of spans of these zigzag morphisms, you can prove what's called a logical characterization theorem, which I'll describe presently, but you'll need strong restrictions on the kind of spaces to which it works. They have to be analytic spaces. But with the cospan definition, we will get a logical characterization theorem that works on all measurable spaces. And you can ask, so why do people use spans instead of cospans? Well, on analytic spaces, the two concepts coincide. So it doesn't really matter which one you use. But with the cospan concept, you can work with them with all measurable spaces. One can argue that anybody in their right mind would want to use an analytic space, but still it kind of identifies what's the real mathematical concept that the cospan captures. In fact, recent results, not by me, but by other people, show that the theory cannot be made to work with spans for general measurable spaces. Okay, so let me give you the official definition of bisimulation. We have these two AMPs, abstract Markov processes. So again, this is a probability triple with a Markov structure on it. And so is Y. So we will say that they are bisimilar if I can find a third object in that category and a pair of not any old morphisms, but zigzag morphisms, in the sense I defined that go like this. So this gives a cospan. Note, by the way, that the identity is trivially a zigzag. So if I have a zigzag from X to Y directly, then I know that X and Y are bisimilar because I can put Y here and Y there and have the identity on this giving me the cospan that I want. Okay, but in particular, it might be that there is no zigzag between X and Y, but they both have zigzags into a cospan like this. So how do we know that this definition makes any sense? We're trying to talk about some notion of behavioral equivalence between processes. How do we know it's transitive, for example? So the basic technical fact is that this category of abstract Markov processes has pushouts. And furthermore, if the morphisms in the span are zigzags, then the morphisms in the pushout diagram are also zigzags. So we can explicitly construct pushouts in this category. This is just a definition of what pushout means, I guess. And this is the co-universality property of pushouts. So I have maps like this. I can construct a pushout in such a way that if I find another object with commuting with morphisms like this that make everything commute, then there's a unique morphism like that that makes everything in this picture commute. So the point is, if alpha and beta are cospan or zigzags, then this delta and gamma will be zigzags as well. So this tells you that you can now actually compose bisimulations. So if X and Y are bisimilar because there is a cospan into a third thing W, and Y and Z are bisimilar because there's a cospan into Y, then I can do a push out of this span and get a sixth object, V. And furthermore, because these were zigzags, zeta and eta will also be zigzags, and the composite of zigzags is also a zigzag. So now I have a cospan linking X and Z, and that tells me that they are also bisimilar. In short, bisimulation is a transitive relation. Now we talk about minimal realization. So we're talking about spaces on continuous state spaces and things like that. So it's obviously not a notion based on counting the states. So we want to look at a bisimulation equivalent version of the process, but yet, so it has to be smaller in some sense, but it has to be doing exactly the same thing. It should have the same behavior. So, and what does it mean to be the smallest realization? So if I have any other process with the same behavior, it should somehow contain this smallest one embedded in it in some way, but actually it's not going to be embedded in it. It's going to be kind of a co-universal property, so it's going to be quotiented into this one. Okay, so I'm going to give a technical definition of bisimulation minimal. Given such an AMP, a bisimulation minimal realization of this abstract Markov process is another abstract Markov process, which I'll call x tilde, and a zigzag, eta from x to x tilde, such that for every zigzag from x to another amp, let's say y, there is a zigzag from y to x tilde, with eta being given by gamma composed with beta. So what this is saying is that if you think of this zigzag as defining a quotient of the original space, then x tilde is the most collapsed version that you can construct for x, because any other attempt to collapse x to y, you can always further collapse y to x tilde. So this tells you the sense in which x tilde is really the smallest one that has that realizes the behavior of x. So one of the things we proved in our paper was an existence theorem which says, give me any amp, there is indeed a bisimulation minimal realization of it. And basically you have to intersect all the event bisimulations to get a smallest event bisimulation. And then the associated equivalence relation forms the quotient in question. Now, two things that you can show relatively easily is that two amps are bisimilar if and only if their minimal realizations are isomorphic. So in some sense, the minimal realization is somehow a canonical presentation of the Markov process you have in mind. Okay, so let me apparently switch gears for a while, because what I'm going to say now seems like it has nothing to do with approximation or bisimulation. So one of the things we did early on in this subject is prove a logical characterization theorem. So given a Markov process, we define a simple modal logic written like this. So a constant in this, so this is an inductive definition of the logical formulas. True is a formula. The conjunction of any two formulas is a formula. And then there's a modal formula like this, which is annotated with an action of the transition system together with a rational number between 0 and 1, which we've written as Q. And the way you think of this is that we'll say a state satisfies a formula in the traditional sense. So any state satisfies the formula true. So the set of states that satisfy true is simply the overall space. The set of states that satisfies the intersection, the AND of two formulas is just the intersection. But the states that satisfy the modal formula, diamond A, Q, psi, are the states such that with probability at least Q, this rational number, after the transition by the action A, you will satisfy psi. So this is a one step into the future look. So this is a very sparse modal logic, one kind of diamond operator that tells you what happens one step into the future, just conjunction, no negation, no negative formulas of any kind, no disjunction. Nothing that says in a state you cannot perform this action. So everything is a positive formula. It turns out that we were able to show that, is that what my next thing says? Yes. We were able to show that two states are bisimilar if and only if they agree on all the formulas of this logic, which is actually a very nice thing, because if you want to show that two states are not bisimilar, you just have to look for a formula on which they disagree. And the theorem guarantees that they will be one such. And in fact, this led to many other interesting things. So for example, we were able to define not just a notion of bisimulation, but a notion of metric that tells you not just that two states are behaviorally equivalent or not, but also how far apart are they? And we can kind of quantitatively measure the distance by saying, well, if it takes a huge formula to distinguish them, then they're in some sense very close. Whereas if they're distinguished by a very short formula, then very quickly their distance gets exposed. Okay, so that intuition can be turned into a precise definition of a pseudometric on behaviors. And the kernel of that pseudometric will in fact be bisimulation. In this setting with the abstract Markov processes, if you look at this sigma field generated by the logical formula. So what that means is, for every formula, you have associated a set of states that satisfies it. So the formulas define a set of states, a collection of sets of states. Each formula defines a set of states. So this set of states we'll call the definable sets. And now, if you look at the sigma algebra generated by those definable sets, this is the smallest event by simulation on X. So this is a theorem. And in effect, this says that this thing characterizes by simulation for this Markov process. So the sigma field obtained on X by the smallest events by simulation is precisely the sigma field we obtain from the logic. So this is the version of logical characterization of event by simulation. Our original proof, which was stated in terms of the span definition, required a lot of technical arguments that utilized properties of analytic spaces. Whereas here, it was actually a much simpler argument that worked on general measure spaces. And it shows that this event by simulation concept is much better adapted to the measure theory structure. Okay, so finally, let's put all this together. So the logic actually gives us an avenue towards approximation. So we see that by simulation says you agree on every single formula. So now you say, okay, let's say I don't want to agree on every single formula. I just want to agree on some of the formulas, maybe the short ones. So then I'll get something that's not going to behave like the whole process, but maybe it's sort of like the whole process because at least on the short formulas that I'm looking at, it looks the same. And maybe if I took a more refined look, I would see that it's actually not the same. So this leads us to the notion of a finite approximation. So let's X be an abstract Markov process. So the first thing we're going to do is to take a finite partition of the unit interval with each of these Qi's being rational numbers. So we'll call these things rational partitions. And we're going to define a finite family of finite pi systems. So pi system is just a family of sets closed under finite intersections. Seems like a fancy word for such a simple thing, but pi systems actually play a very, very important role in measure theory. For example, if you look at two different, or you're wondering if two measures are different on a certain sigma algebra, and the sigma algebra happens to be generated by a pi system. So the generating sets form a pi system, just required to be closed under intersection. So a typical example is the Borel sets on the real line are generated by the open intervals, and the open intervals are a pi system because the intersection of two open intervals is an open interval, or else empty set. Now, if two measures actually agree on the generating pi system, they agree everywhere. That's a fantastic thing because it tells you if you're wondering whether two measures are actually the same, it suffices to prove on the real line that they agree on intervals, on open intervals, and you're done. So that's why pi systems, though apparently so simple, really play a fundamental role. Okay, so we're going to define a bunch of pi systems here. So the crudest pi system just has X and the empty set. But then we're going to say, well, we're going to look at these numbers Q1 through Qn, and we're going to look at the inverse images of these half open intervals, Q sub I up to 1. So these are the things that land in the set A with probabilities somewhere in that range under the action A. Now, what are the things that I'm going to use for A? I'm going to use some of the sets that I've constructed before. So my crudest construction just has the whole space and the empty set. At the next level, I'll say you have to have some transition into the whole space or the empty set. And then I keep unioning those and constructing more and more refined families. And these will all be closed under finite intersections. Why is it a pi system? It's because basically I put and in my logic, which is the reason why and was there. Okay, so this notation pi means close under finite intersection. So I've got these family of finite pi systems. And as I put more and more points and refine these partitions and make the blocks smaller and smaller, I'll get more and more of these sets. So for each pair consisting of a rational partition P and a natural number M, we'll get a sigma algebra, which is the sigma algebra generated by that set capital, by this family, the pi system that I've constructed. So this is the sigma algebra generated by phi. So we call each of these pairs an approximation pair. And the crucial fact is, if you take the sigma algebra generated by the unions of all these things, then effectively in the end, you've got all the formulas. Okay? And this is precisely the sigma algebra obtained from the logic. So how do we relate these finite approximations? So I'm going to say P of M is less than Q of N if N is bigger than M and Q refines P. So Q has all the points of P that partition the interval, but may have more. So it's got it into smaller pieces. And obviously, I'm looking at more of these sets. So now, if I look at the sigma algebra generated, then there's a natural morphism, which is just the identity map on the underlying set. But in this direction, it's actually measurable because this is a cruder sigma algebra and this is a finer one. Okay, so because this is an inclusion of the sigma algebras, and both of them are sub-sigma algebras of the big sigma algebra sigma, this is a measurable set. So this is a well-defined inclusion. And furthermore, if I have a chain of these refinements, then these maps compose. So in short, we have a projective system of these maps indexed by a poset of approximation pairs. Right, so we have this whole family of approximation pairs. They're a directed family. And if we look at the associated sigma algebras and approximate Markov processes that we've constructed, we've got a projective system of these maps. Okay, so notice what we have done. We've kind of developed this notion of approximation not by collapsing the state space and so on, as many people have done before, or carving it up into pieces, but we've done it by coarsening the sigma algebra. And of course, then we refine the sigma algebra to get better and better approximations, but the whole approximation is guided by the sets in the sigma algebra and not by the points of the space. So we can quotient the space X by the equivalence relation that identifies 2 points that cannot be separated by measurable sets. So if you want the point set version of it, this is what it is. But again, it's really being mediated by the sigma algebra. Now, these sets are going to have finitely many points, these quotient sets. So the quotient map induces a projected version of the lamp, the labeled abstract Markov process tau. And when these approximations are refined, the quotients compose. So we can define maps between the quotient spaces. So here is a fragment of the big projective diagram that we get. So here you see we have Qn defines the approximation pair Pm. That was the map we had before, and now we're quotienting it by the equivalence relation I induced before. 2 points are identified if they cannot be distinguished by any set of the sigma algebra. So now I have these finite sets, and I have this induced map down here between those finite sets. So basically I get 2 projective diagrams. So one is actually happening in the category of labeled abstract Markov processes. And the main theorem is the probability spaces of finite approximants, each equipped with a discrete sigma algebra indexed by the approximation pairs, forms a projective system in the category rad equals. This system of finite approximants has a projective limit in this category rad equals. Now, this theorem, which I'm not going to spell out, has a number of parts, but it uses a theorem by Choksi from 1958. So Choksi is a distinguished measure theorist from the 50s. By sheer coincidence, it turns out his house is about 10 doors down from where I live right now. So of course he's long since deceased, but I didn't live here when I proved this theorem, but I moved into the same block in which he lived. But anyway, so Choksi's theorem from 1958 was called a projective limit of compact Hausdorff spaces. And if you look at what he proves, he constructs the required limit. So we were very grateful for that, but he does not prove the universal property that we should have proved. So we had to do that. And I think in those days when analysts said we have a projective limit, they didn't really, I mean, they must have been aware because they really were constructing things that did satisfy the universal properties, but they certainly didn't prove it. Anyway, clearly he must have been thinking that, because why would he construct it to have that universal property? But it was not completely routine to prove that it had that universal property. But anyway, the point is, all our family of finite approximants forms a projective diagram and has that projective limit. So here is, roughly speaking, what the situation looks like. We have these, this is a fragment, of course. There's a whole family of these things linked together. But now there's a projective limit up here that forms a universal cone, so that anybody else masquerading as the cone, there will be a unique morphism like this into there. And that unique morphism is all happening in rad infinity, sorry, in rad equals. So it preserves all the measure structure, all the measures, the sigma algebras, everything like that. And notice I carefully didn't say it happens in AMP, because it doesn't preserve. We weren't able to show that we get a universal property in the category of abstract Markov processes, only in the category with the measure structure. We can now consider, how do we put abstract Markov process structure on it? We don't get a universal property in the category of abstract Markov processes. Actually, we might, we just haven't succeeded in proving that. However, the universality of the construction in rad equals almost forces the structure on the projective limit constructed in rad equals. So a lamp can be defined on the projective limit constructed in rad equals, so that the cone formed by this limit object and the maps to the finite approximant actually yields a commuting diagram in the category AMP. So we're this close to actually constructing the projective limit in AMP itself. And I think actually this thing is that, but maybe it requires more high-powered analysis tools than we've used. So we've tried a number of things like martingale convergence theorems and so on to prove that this is actually universal, but that's still open. Now you can ask, so you've constructed these finite approximants and you've got something. What is it? And what we were able to show, that the lamp obtained in this way by forming the projective limit and then defining the lamp that I've described is actually isomorphic to the minimal realization of the original Markov process. So this is telling you that these finite approximants are actually converging to the original process that you wanted. And in some sense, you can get arbitrarily close just with the finite process. So this gives a nice connection between the approximation process and the minimal realization theory. Really, we have two routes to minimal realization. One is through this projective limit of its finite approximants, and the other, of course, is through the logic. Okay, so I will stop there. So let me summarize what we have done. I've elided a lot of tedious calculations to prove that we have, the co-universal property of Pushouts and the universal property of the projective limits and so on, but these details can be found in the paper. But all these three talks have all emphasized a dual view of Markov processes as Markov operators. Instead of transition kernels that take a measure and transform it to a new measure, we're looking at things as transformation of expectation values of random variables. This is roughly the way to say it. The conditional expectation gives us a tool for constructing averages. which is exactly what conditional expectation is supposed to do. So when you condition on a coarser sigma algebra, you've kind of smoothed out or averaged over the sets of that coarser sigma algebra, and this allows you to give approximations. And we exploited that here by saying, let's look at these very crude sigma algebras that come from the formulas of the logic, but we're only looking at finitely many formulas at a time. And as we expand the set of formulas at which we're looking, we get better and better approximations. And nicely, these approximations actually organize themselves into a projective diagram for which the projective limit actually exists. And that projective limit actually reconstructs not any old thing, but the minimal realization of the original process. So let me just mention some related results. And I see I'm missing a letter S. It should be results. This is not some funky French word. So we talked about L1 and L infinity in the early part of the talk. And you might think, well, could I have defined an LP, LQ version? So indeed, I set one of my master's students to work on this, and he did it. Actually, he was an undergraduate at the time. So he rolled up his sleeves and just did all the analysis necessary. It was very similar, but there were technical details were a bit different. And we didn't think this should be another paper, but we thought it should appear in some form. And JACM advertised that they had electronic appendices. So you could, if you have an accepted paper in JACM, you can then add appendices of related work later on. So we thought this would be perfect for that. We submitted it to them. They said, yes, very good. We accept it, and disappeared into a black hole. I've never seen it on any JACM website. I've searched for it. I've sent numerous emails to people saying, where is this paper? So if you want it, you'll have to ask me. And maybe I should put this version on my own web page. But anyway, it has been developed. It's quite nice. And it was actually very impressive that an undergraduate student could do that. He's a very impressive undergraduate, as you might imagine. Speaking of duality theory in the context of Markov processes, quite independently of all this line of work, with completely different, I think, disjoint set of co-authors, I've worked with Dexter Kozin, Radu Mardare, Robert Ferber to develop a duality theory, a stone-type duality theory for Markov processes. So we called the algebraic counterpart to these we call Aumann algebras. I don't know if many of you have heard of Aumann, but he was one of the pioneers of probabilistic modal logics and actually has a Nobel Prize in economics because he was working on, I guess, rationality, epistemic logic, and economics and things like that. So modal logics. Anyway, so we developed a stone-type duality for modal logics based on the same kind of modal logic that you saw appearing in the logical characterization theorem here, but the mathematics is quite different. It's really like stone spaces equipped with Markov structure on top of it. I'm vexed by the fact that we have not succeeded in proving that we have a projective limit in the category of Markov processes. I'm sure that the thing we constructed really has that universal property. We've just failed to prove it, and maybe I should spend some time learning more analysis and doing it. So we've been dancing around this, all of us, from time to time, but it's still open. If anybody does it, please let me know. And lastly, my student Florence Clerc has been working for a while now on her PhD thesis is on developing bisimulation concepts for continuous time and continuous space processes. So all these things where I talked about continuous space, the space was continuous, but the actions, the transitions were discrete temporal jumps. You perform an action and you jump to a new configuration. But she was interested in things that flow, governed by perhaps diffusion or some related thing. So the general class or a general class of well-behaved processes of those kind are called Feller-Dinkin processes. And she has developed a theory of bisimulation for Feller-Dinkin processes. And she's now using this kind of stuff that I described today to try to develop an approximation theory for those Feller-Dinkin processes. so which is still under construction. So if you are interested in her work on simulation for continuous time processes, which by the way was incredibly much more difficult than we thought it would be, and not just some tinkering with the theory that we've developed so far. You can look at the last two versions of the MFPS conference, Mathematical Foundations of Computers of Programming Semantics, where she had papers in 2019 and 2020. Okay, I see I'm bang on 1 o'clock, so I will stop here.
Thank you very much. That was very interesting, actually. All right, so are there any questions? If you have, please raise your hand or write in the chat. Maybe in the meantime, I'll ask an unpleasant question.
Uh-oh.
So you say that there's a problem in proving the universal property in the category AMP of this limit.
I didn't say there's a problem.
But you did prove it. So, I mean, what fails here?
Nothing fails. I think it probably is universal.
Or like, okay, what is difficult? What's the missing link?
Missing link is I just can't prove it. I mean, I'm sure it is. I'm sure it is universal, you know, and we try to construct that morphism that that universality should give you. So we have a morphism in the category rad equals, then we're trying to prove that, oh, well, this thing is also a zigzag.
Oh, so what? Okay, so what remains to be proven is that the morphism is a zigzag, or?
Yeah, so it respects the Markov structure. So it preserves all the other structure, and then if you look at this thing and say, okay, I have this thing, how do I construct this in such a way that it preserves the zigzag structure? It's kind of forced on you. So that's why I think well, this is a intuition for why things are universal. When you see that you have no choices, that means it must be universal in some sense. But, you know, it's just my analysis toolkit is just deficient. So we learn a lot of analysis trying to prove it. So I learned martingale convergence and stuff like that, trying to prove it. I just not clever enough. What can I say? But I don't think there's an obstacle. I think it really is. It is true.
I see.
Maybe younger, smarter people like you can prove it.
I don't think I could prove it, but I wondered what the problem was.
I don't think it's a big problem. I just think, I mean, look so close. I mean, it's just that we're doing lots of other things now, so it's not like I can turn around and devote a lot of time to it. We did devote a lot of time 8 years ago when we were getting this ready for publication. And after that, maybe once or twice, we tried for a few days at a time. Maybe it just requires, I now actually think I know a lot more than I did. And maybe if I try again, it'll happen. Who knows? But it was super annoying because it's not like there's an obstacle I can say, it's not universal because of this or that. I just think it is universal and just too dumb to prove it.
I see. So Alex Goodlad seems to have a question. Alex, when you're ready, feel free to unmute yourself. Are you ready?
Yeah, I'm more or less ready.
Okay.
So I guess my main question is, I literally just heard of your work, Prakash, like 2 days ago, and I'm kind of fascinated and actually like and you know it relates to what I've been trying to find all my life, which is how can I, because I'm interested in analysis and logic, and I'm having trouble, you know, figuring out a way to do a thesis with Larry Moss is my advisor, if you've heard of him.
Larry's a good friend. So
I guess the question kind of, yeah. He sent me the email. So I guess the question is, I can't help but notice that you did, I think, a chapter in Jan Ruten's book about coalgebra, and
yes,
and you mentioned bisimulations of Markov processes. So
my chapter was on probabilistic bisimulation.
Yeah. So what I'm kind of wondering is, I guess I have two questions. The first is that so the bisimulations, do they give rise to like a co-induction that you can do on certain coalgebras that are given rise from the Markov processes themselves? So there's certain like polynomial D functors is what I'm familiar with, those coalgebras, and the initial, or sorry, the final coalgebras exist, and the kind of a problem I think has been solved, but I'm not familiar with the papers, is the co-induction. So that bisimulation relation you talked about, that is kind of what we need to do that. That's the first question. And the second question is, I guess, what how is kind of all this stuff that you do, has it been used much in applied, more kind of applied probability and things of analytic nature that you're aware of? So yeah.
So obviously we should talk more.
Yeah.
I'm very happy to make your acquaintance. As I said, Larry is a very good friend of mine. But anyway, so the first question was about co-induction principles, right? So
yeah.
So bisimulation, so what I'm describing is kind of a dualized, everything is dualized. So things have become expectation value transformers instead of state transformers. But in the state transformer view, people have indeed proved the existence of final coalgebras. Bisimulation, the bisimulation minimal version is of a process is exactly its image in the final coalgebra. So this is well known. And in this dual view, it should all work similarly or even better, but we have not spelled out the coalgebraic connections, but it should surely be there. And if that's what you want to do for part of your thesis, I would love it. But so I think that's a nice thing nice question and a nice thing to do. But almost surely, gosh, I mean, informally, not in the probability sense, almost surely this thing also ties up with final coalgebras.
I see what you did there.
The second question, sorry, I've forgotten the second question. What was that?
It's kind of what are the...
It has been used in practice.
Yeah.
So that causes me to
Sorry to ask that question.
No. So a lot of people who do practical things praise my work and never use it. So so people I won't name, but you know, there's this person who's famous for her work on probabilistic model checking, maybe the world leader, and she always puts up a slide with my name on it and says, Prakash has done this great stuff, but I've never actually seen it impacting anything she's doing. So I don't know, maybe practical people have admired it, but not to the extent that they want to use it. One of the obstacles is, what's a good computational representation of a continuous space system? I mean, it's, you know, discrete space system, you can enumerate the states and do this, that, and the other. How am I going to describe for you a diffusion process happening in R3 in a way that is accessible to computation?
And modal logic, sort of like corresponding it to modal logic doesn't really help with that?
Not in a way that I've seen, but if you have ideas, I'd love to hear them. However, one thing that has had impact in practice is that I mentioned briefly in passing metrics between Markov processes, bisimulation pseudometrics. So the machine learning community has jumped on this. And in fact, for the last few years, I am a machine learning person now. I'm still doing the same thing that I'm doing, except I've now branded as a machine learning person. And I've actually published in machine learning conferences. I think all my publications in 2020, no, that's not true. So I had a publication with Florence in MFPS, but many of my publications in this year have been in machine learning. So one in ICML and one in AI stats. And the AI stats paper is really exploiting metric structure, the notion of coupling, bisimulation, and so on. So this word bisimulation is now known in the machine learning community. Of that, I'm quite pleased. and bisimulation metrics. And of course, like so many other things, somebody in machine learning actually came up with bisimulation independently, well after all my papers, and well after 2 decades after Larson and Scoe. And the people who did that work cited Larson and Scoe, but the other machine learning people don't. So they always cite the machine learning people who came up with it. But we were the first to publish in the machine learning community on bisimulation metrics. And so at least I get cited by machine learning people as inventing bisimulation metrics. And that seems to have quite a lot of impact. I mean, nobody has yet built a neural net based on it, but there are neural nets, generative adversarial nets based on what's called the Wasserstein metric. I say what's called the Wasserstein metric because it should be called the Kantorovich metric, but that's a different discussion. But they have used this for, all kinds of real tasks. I mean, one thing about the machine learning world is you might have a paper with 5 nice theorems, but if it doesn't have a few graphs, it's not going to get in. So you're forced to do something quasi-practical. And so that's the direction in which I'm going for practical applications.
Okay, very nice. Are there any more questions? So Prakash, if you have time, I have another small question. So you mentioned that there's a pseudometric on behaviors.
Yes.
Could you say a little bit more on that?
You want part 4?
No, I mean not, but
no. So I gave the intuition quickly. I'll repeat that. So
so yeah, for example, I didn't understand if it's symmetric or not.
yes, it is. It's a metric. It's a pseudometric.
Okay.
It obeys triangle inequality. So unlike horrible things like the KL divergence, which is neither obeying triangle nor symmetry, this thing is a proper pseudometric. So what it does, so you know what I mean by pseudometric. It allows points that are not identical to be at 0 distance. So this pseudometric has the property that its kernel is in fact exactly bisimulation. So when points are at 0 distance, they are in fact bisimilar. And so if you quotient by simulation, it'll be exactly a proper metric. And the intuition, which is not exactly correct. Okay, maybe instead of the intuition, I'll tell you somehow how it's defined. So one way of defining by simulation is you define an appropriate functional on the complete lattice of relations. And what this functional does is you say, you do one-step unwinding of the dynamics and then you look at the relation. Okay, and that defines, so that defines a map from relations to relations. You can show that this map is monotone, it has the greatest fixed point, therefore, and that one is by simulation. So the way we define the metric is we say, okay, we're going to define a metric between points. So you look at the transitions, you look at the induced Kantorovich metric on those distributions. From this, you define a map from metrics, from pseudometrics to pseudometrics. We prove that that thing is monotone and has a greatest fixed point. And that one is our bisimulation metric whose kernel is the metric. And that's also closely related to final coalgebras computed in the category of metric spaces. So in fact, so that was mostly done by, not by, so we were the first to actually define the metric, but a much better definition and a much smoother treatment was given by Frank van Bruegel and James Worrell, who then even connected this metric to the transshipment problem and gave algorithms for computing it and stuff.
I see, nice. So okay, it's really like Kantorovich based.
Totally, yeah, nice. Totally Kantorovich based. And so we extended that to MDPs, which is when the machine learning people paid attention.
Nice, yeah, right. Thanks. Okay, are there any more questions or comments?
I guess I have another, which is what's the paper in the introduction? I missed the first part of the talk. And I'll also send you an email just in general about papers that I'd be interested in that I can't get elsewhere. But
yes, please send me email because we should certainly stay in touch.
Yeah.
And I will send you, well, I can answer your questions in more detail perhaps, and send you relevant papers. But the paper that I'm referring to on which these 3 talks are based appeared in JACM in 2014.
Wait, not because there's that paper that was in a black hole.
No, so the paper is not in a black hole. The appendix to the paper is in a black hole.
Okay.
So the paper got published in JACM, and then this wonderful electronic appendix thing is the black hole. I don't know. I haven't looked recently. Maybe it's there, but certainly for several years after, it just disappeared.
Okay, thanks.
Come.
Okay, anybody else? Okay, seems there are no further questions, so let's thank our speaker again. Thanks, Prakash. That was a very interesting talk.
Thanks for stopping by.